The next thing that we're going to talk about is the differentiable. The differentiable is just a fancy name for that dy. There's also a differential dx. Now, treat dy and dx basically like variables. We've been saying for a long time that if you write dy over dx, that's the derivative. You could also write y prime. You could also write f prime of x. We're using all of those things as our notation for a derivative. Well, ignore this for a second. This is just a division symbol. So why can't we just multiply both sides by dx? Or in this case, divide both sides by dx. The two dx's would cancel on this side, and we'd be left with dy over dx equals f prime of x. So we can treat these as separate variables, which is kind of neat. So in this one, I want to figure out what dy is. I don't want to find dy over dx. I want to find dy. So to do that, I'm going to take the derivative of this thing, because if I take the derivative with respect to x, I'll get dy over dx on that left-hand side. And then I can just move the dx over to the other one. So I want dy equals y prime times dx. So I just need to find the derivative of y. So let's see, I got to do product rule in there because I'm trying to take the derivative of this. So that is going to be 2x, derivative of the first times the second, ln of x, plus the derivative of the second, which is 1 over x, times the first, which is x squared. Okay. And then all of that is going to be multiplied by dx. Now again, I could have dx over on the left-hand side to start off, or I can just set it up like this to begin with. Let's clean this up a little bit. So dy equals bracket 2x ln of x plus these two, if we brought those together, that is going to be x squared over x, which is just x dx. Cool, we found dy. Great. Now they want to evaluate dy for the given value of x and dx. So that they're saying we're going to check this particular point, x value being 1, and we want to move just a little bit. We want to check what happens, what is the change in our y value as we change our x value by 0.01. We'll just move it a little bit. So we want to just plug those numbers in like you do with any other numbers. So we get 2, our x value is 1, ln of 1 plus 1. And then that dx, we're going to plug in the value that we got. We're going to plug in our 0.01. Okay, now it's just a matter of simplification. In fact, you could probably just type all this into your calculator. On the inside here, we get 2 times the natural log of 1, which is 0, so that's just 0. So we get 0 plus 1 times 0.01, which equals 1 times 0.01, which is just 0.01. Neat. So that is the change in y that's going to happen when we start at x and we change our x value by 0.01. We should expect our y value to change by 0.01 as well. Cool. All right, now this section wouldn't be complete without a little bit of application, and so we're going to do one on percentage error. So, sudden cat. Sudden cat, no, she's over there. We want to start by identifying what's going on in this problem. We've got the edge of this cube measured as 10 centimeters. So I'm going to have that actually act as a variable. There's this edge length, and that's going to be my x. I'm going to play around with that value, but we're going to be looking at a lot of different cubes. So let's just have that be a variable for right now, edge length. And then we're also talking about the volume of this thing. So we're going to have V stand for our volume, because we're also talking in general about our cube, the volume of these cubes. Okay. So it's talking about percentage error and volume calculation. So we should probably also have an equation for volume calculation. So our volume of any cube is going to be x cubed. Now, there is a percentage error. This percentage error is talking about what can happen with that x value. That x value could be off by a particular amount. It could be off by 0.1%. By 1%, excuse me, not 0.1%. So that is going to be our change in our x. Our x can vary, can move a little bit by 0.1%, or by 1%, which is 1%, 1%. Ugh. Then in order to figure out what the percentage error in our volume is, our volume error, change in our volume is going to be dV, volume change. So we've got a change in our x value in our edge length, and we want to see how that relates to the change in our volume. So we're going to take the derivative of this thing to figure out what's going on. And we're going to do it kind of with that differentiable version, where we've got dv. Actually, I'm going to do it the more classical way. dv over dx equals what? We've got 2x squared. But if we want to kind of like really isolate, because we want to figure out that volume change, I want to get rid of that dx. So I'm going to multiply both sides by dx. So you get dv equals 2x squared dx. So the thing I really wanted to figure out is what's going on with that change in our volume because of the error in the change in our edge. So we didn't want dv and dx together. We wanted to separate those two variables from each other. So the edge length that we're dealing with right now is, now we can start putting in these numbers, is we can put in 10 for our edge length. And then we also want to put in our error of the edge. To put that in, we need to take into account that edge length, because if we were measuring a cube that was 100 centimeters and our error was 1%, then we would be a centimeter off. But that's not how big our cube is. A cube is only 10 centimeters. So if we had an error of 1%, it's going to be off by about 0.1 centimeters, as opposed to 100 centimeter cube is going to be off by 1 centimeter. A 10 centimeter cube with an error of 1%, we're doing 10 times our 1%. We get 0.1. So our dx that we're going to be putting in, it's 1% times that 10 centimeters, which gets us 0.1. Now we fill in the rest of the equation. We got squared and we got a 2. This ends up spitting out a value. I brought that 2 down again. I can't take derivatives, apparently. I get too excited about that subtracting 1. I think that's what's going on. So let me slap a 3 in there. Sorry about that. So we get 100 times 3, which is 300, times 0.1, which is going to drop off a 0. So we get 30 is our dV. So that's how much it is going to change. In order to figure out that percentage error, you want to say, okay, we're going to be off by 30. So we're going to lose 30 points. We're going to be off by 30 points of what our original volume would have been. So I actually need my original volume for this one, because I'm going to be off by about 30. But 30 what? Because what is the original volume? If I just know it's off by 30, that could be a little if it's like 1,000,000 cubic centimeters, or it could be a lot if it's only like 20 cubic centimeters. So how big's my original cube? I want to figure out dV over V. So my original cube is x cubed, and I got a 10 centimeter cubed. So the original volume of this thing, if I had done everything perfectly, is it would have been 1,000. 10 times 10 times 10. But I know that I'm off by a little bit, so that thing is going to shift by a particular amount. It's going to shift by 30. Could be more, could be less. So type that into your calculator, you get 0.03, which is 3%. So that is our percentage error. And I think that's it for today. Yeah, so this linearization, it's just a fancy version of point slope form, but we've kind of brought one of those y values over, and we're using derivative as our slope in that point slope formula, which makes sense because that's what a derivative is. It's finding the instantaneous slope of a curve, but then we're able to take these curves and kind of make them into straight lines. Finally, that differentiable is starting to play with this idea of derivatives dy over dx as separate variables, and we're going to be playing with them more as variables in the coming minutes. Thanks for watching. Have a good day. Bye-bye.